Welcome to our paper HyP-NeRF, Learning an Improved NeRF Prior using a HyperNetwork. We first start with some applications. In the first application, we take a text prompt, and in the second application, we take a real-world example of a cluttered scene, use SAM to find the mask of the object of interest and generate a NeRF from it. HyP-NeRF can easily generate high-quality NeRFs for such multimodal inputs. For example, generating an avocado chair that looks like an avocado in terms of the shape, as well as the color. HyP-NeRF is a novel latent conditioning approach that uses a hypernetwork to predict multi-resolution hash encodings that transform the positional coordinates to instance-specific encodings, along with the multi-layered perceptron of a NeRF instance. This instance-specific multi-resolution hash encodings allow us to predict high-quality NeRF instances. Here we show the difference between HyP-NeRF, on the left, against a hypernetwork that only predicts the MLP parameters, on the right. The difference in quality is clearly visible. A key property of our network is that we operate directly in the NeRF space, allowing us to render at any resolution. As shown, HyP-NeRF preserved details even at a high resolution of 1024. Now we briefly talk about HyP-NeRF architecture. HyP-NeRF relies on a codebook where each code corresponds to a training instance. During training, HyP-NeRF trains over many NeRF instances and learns a prior over NeRF representation. We first start by comparing HyP-NeRF against instant NGP. Next, we perform single-view NeRF generation to validate if HyP-NeRF can render novel NeRFs unseen at the time of training by considering the task of conditional NeRF generation. Given a single-view image, we use test time optimization, as explained in the main paper section 3.2, to obtain the NeRF. As can be seen, HyP-NeRF generates detailed outputs true to the single-view image while preserving minute details like lighting conditions and brightness, whereas Pixel NeRF improves near to the input view but deteriorates from novel poses. This indicates that HyP-NeRF has learned a strong prior capable of modeling high-quality NeRFs unseen at the time of training. However, the output NeRFs have uneven texture and structure. To fix this, we propose denoising and fine-tuning. In this, we first render the predicted NeRF from multiple predefined poses. Next, we denoise the rendered outputs frame by frame using an image-level denoising network. We then use the denoised output to fine-tune the initial predicted NeRF to improve the quality. Here we show some results of denoising plus fine-tuning. As can be seen, our denoising strategy significantly improves the quality of the predicted NeRFs while relying on simple image-level denoising networks. As we only fine-tune the predicted NeRF and do not optimize a NeRF from scratch, the output is geometrically consistent even though the image-level denoised outputs may have minor inconsistencies. Now we show the results of querying the prior learned by HyP-NeRF using different modalities. For example, here, we generate NeRFs conditioned on text. As can be seen, HyP-NeRF can generate NeRFs based on different descriptions while adhering to fine details like the color and the described pattern. Next, we show results on cluttered scenes. In this, we chose an object of interest and use SAM to segment it. We get occluded, in the wild, single-view novel object instance. The outputs shown are generated in a single forward pass, rendering the NeRF's parameters in less than a second whilst generating high-quality outputs even from such challenging real-world inputs. Even here, although the input is highly occluded, the output maintains the structure, colors, and overall characteristics of the input. In these examples, we use a query network as described in the main paper section 3.2 that uses a CLIP-based mapping network to encode the multimodal text and image inputs. However, as we rely on pre-trained CLIP encodings to encode the input image, we may lose out on the most finer details in the encoded representations. For instance, in this example, the handles or color of the legs. As our future work, we aim to design an improved mapping network that can encode fine details, for example like in test time optimization, and map to our non-standard prior to generate the high-quality NeRFs in a single forward pass. We now make some more comparisons with instant NGP that relies on multi-resolution hash encodings to optimize over a single NeRF instance. On the other hand, HyP-NeRF conditionally predicts instant-specific multi-resolution hash encodings and learns a prior over thousands of NeRF instances. We close our supplementary video with additional results of test time optimization. Here, we render NeRFs from single view with heavy occlusion. As we operate directly in the NeRF space, we can perform the optimization by only sampling rays in the non-occluded regions. As can be seen, HyP-NeRF is robust to occlusion and can render detailed and high-quality NeRFs even in such challenging circumstances. Thank you for watching our video. We hope you had a great time viewing the results.